In this video, we continue talking about OpenGL. We'll make sure that you start watching YouTube videos posted by Nick, Machine Learning Acceleration Performance Engineer in San Francisco Bay Area. And the first video here covers chapters 1.1 through 1.4. And it's talking about computer abstractions and technology. Our presentation today introduces OpenGL shaders. And shaders are programs that run inside graphics hardware. So in 3D space, each vertex represents a single point, and of course has coordinates x, y, z. If we'd like to create a triangle, of course we have to make it from 3 vertices. Right here we show like A, B, C vertices in space. Triangle forms a simple face, and of course triangles are effective because they place themselves in the plane, and the vector which is perpendicular to that plane is called a normal. So this vector here is a normal vector to the plane in which we lay this triangle. Now here it's shown that this vector can be actually computed as a cross product of CB and CA, and more about this later when we talk about vector math later on. Each vertex, on the other hand, can also specify a normal. So typically coordinates such as x, y, z, and also information about a normal vector would be considered in OpenGL a vertex attributes. So normals and coordinates are vertex attributes. Well, triangulation is emphasizing that geometrical shapes in 3D space can be made up of polygons. But OpenGL does not support polygons which have more than 3 vertices. The only polygon that OpenGL supports is a triangle. And so that's why all shapes that we create, like this cube or box, have to be triangulated. So you can observe that each side of this box is actually made up of 2 triangles. It could be using more triangles, but it has to have at least 2 triangles. So if you have a rectangle like this, typically it's described by 2 triangles. So the process of creation of these triangles based on the vertices that we specify is called the process of triangulation. And triangulation typically is done for us by modeling software that allows us to model our objects in 3D space, and it automatically computes normal vectors and all the triangles that will create this 3D shape. So programmable graphics pipeline is an important aspect for us because we have to understand where our graphics programming is taking place. Modern graphics hardware allows access to its graphics pipeline and make it programmable. So OpenGL uses shader programs to do this kind of programming. So in this demonstration here, we start with our geometry that we load into memory in the form of like array of numbers. So we have a lot of numbers that describe our shapes. So each individual square here represents an individual vertex, right? So we could have like this cube modeled, and we have its geometry, and every vertex that is making up this shape has its coordinates described here, and other vertex information can be also part of this. So these vertices as an array in computer memory is loaded into graphics hardware, and then the vertex shader starts to execute. So this vertex shader takes this original geometry, this, right, and then examines each individual vertex. And vertex shader is executed for each vertex that we supply. Okay, so this program is executed for every single vertex that we have. Like we have these vertices in this box, and the vertex shader will be run as many as 8 times, because we have actually 8 vertices that make up this specific shape. So then what happens is that vertex shader, what it does, it does the necessary transformations. So you remember that we already discussed that we can basically rotate this shape, and these rotations compared to the original geometry are all computed by the vertex shader, because the position of every vertex is recomputed as we do necessary transformations. So once the vertices transform in space, and of course we can also scale this, make it bigger and smaller, there are multiple transformations, move it, and then the primitives are assembled, and it's basically the individual vertex arrays are assembled into triangles. So we can also program our geometry, we can reprogram our triangles, but this is not what we're going to do in our course. Remember, rasterization generates individual fragments that will eventually make themselves visible as pixels. And rasterization produces these fragments, which are pixel candidates, which don't have colors. They are uncolored. And then the fragment shader is another program in OpenGL graphics pipeline that we're going to use to assign colors to individual fragments. So then, once we have that, we have to make a projection on the surface of our screen, and we begin to visualize actual pixels and start showing the actual view, so that the user can see the result of this processing.